Greetings and welcome back to our YouTube channel. My name is Clinton P. Kui. I am a student at the University of Liberia reading mathematics major with minor in physics. And today we are going to be solving question number 11 on the practice questions for Math 304 midterm exam. And question number 11 says we should find the differential equation whose solution is given by y is equals to a cos omega t plus b sin omega t, and then where a and b are arbitrary constants. So the first thing you need to do is to recognize that a and b are arbitrary constants. Omega is also a constant, but it is not an arbitrary constant. For example, pi is not an arbitrary constant. Pi has a value 3.1415, and that is a constant value. Anywhere in the world it goes, that is the value of pi. The Euler's number E is also not an arbitrary constant because it has a value. And I is iota, the complex number. It is a constant, but it is not an arbitrary constant also. So that's the general idea. A and B arbitrary constant, meaning the values of A and B can change. A can be 5, B be 3, A can be 2, and B is 6, and so on. So to find this differential equation, what we need to do is to begin with the solution. Y is equals to A cos of omega t plus B sine of omega t. And then, since we have two arbitrary constants a and b, we differentiate this particular function twice. Differentiate the function twice. The first derivative we have y prime is equals to a is a constant, so we differentiate cos omega t. Remember the angle omega t. If we differentiate omega t, we have omega, because the derivative of t with respect to t is 1. So the derivative of cos omega t is minus omega sin omega t. So it's a times minus omega sin omega t plus b onto the derivative of sin omega t. The derivative of sin is cos. The derivative of omega t is omega. So you are going to have omega cos of omega t. That is the derivative. So this is the first derivative here. We can just sort of multiply through. We have y prime is equal to a than this. Now, let's move on and find the second derivative. I chose not to multiply through because I'm about to find the second derivative, and you're about to see why. The derivative of y prime is y prime prime is equals to a is an arbitrary constant. We differentiate minus omega sin omega t. But remember that omega is a constant. So we are just going to differentiate sin omega t. The derivative of sin omega t, we already told you, is omega cos omega t. The derivative of sin is cos. So this negative omega is going to remain here, and it is going to be multiplied by omega. So you are going to have negative omega square. Negative omega square sin of omega t. Because you are multiplying negative omega by omega, and that there is not sin now of cos. The derivative of sin is cos, so it's cos of omega t. Good. So the derivative of minus omega sin omega t is minus omega square cos of omega t plus b onto, we want to find what is the derivative of cos omega t. The derivative of cos omega t is minus omega sin of omega t. But that is being multiplied by omega. So omega times this entire thing is minus omega square, and the derivative of cos is sine of omega t. Great. So what you observe here is that we want to differentiate. You want to differentiate for the first time. Then we differentiate for the second time. The derivative of sine omega t, we say, is omega cos omega t. This times negative omega is negative omega square cos omega t. Plus, to differentiate cos omega t, we say the derivative will be negative omega sin omega t. And you take this and multiply omega, you have this. Great. So we just move on and just multiply through. We have This time this is minus a omega square cos omega t. This time this is minus b omega square sine omega t. Very simple. Now, we have y to be a omega t plus, or a cos omega t plus b sine omega t. In the derivative for y prime prime, the second derivative, we can factor out, because here we have minus a omega square, we have minus b omega square. So we can factor out a negative omega square for the entire thing. So we have y prime prime is equal to minus omega square parenthesis open. If you take out minus omega square, you'll be left with a cos omega t. And then the negative is already out. Omega square is already out. So you'll be left with plus b sine of omega t. That's what you're going to have. You factor out an omega square from the numerator there. So once we do that, what do we expect to have? We know that the entire expression down there, so this entire thing is actually y. So you have y is equal to cos omega t plus b sine omega t. That's what you have. So we replace this entire thing with y in this second derivative. So we have y prime prime is equal to minus omega square times a cos omega t plus b sine omega t. A cos omega t plus b sine omega t is y. So this entire thing is y. So we have y prime prime is equal to minus omega square y. We send this across. We have y prime prime plus omega square y equal to 0. Ladies and gentlemen, this is the differential equation whose solution is a cos omega t plus b sine omega t. Thank you very much for watching, and we hope to see you in our next video. Hello YouTube, this is Clinton P. with another tutorial on differential equations, and this series is a series of questions from the midterm practice problems for Math 304 at the University of Iberia, which we call differential equations, and this is question number 15. 17 questions, and we are done with 14 of them. So question number 15 says, if the solution of the differential equation 1 over sine inverse of x multiplied by dy by dx equal 1 is, if the solution of this is y equal x sine inverse of x plus L of x plus c, find L of x. Now, we will solve this problem by using differentiation. We could also solve it by using integration. So differentiate in the sense that we find dy by dx, and then we try to find the value of L of x by integrating after comparing this and that. But what we have to do here is just simple. We just take this, we take 1 over sine inverse x dy by dx equal 1. And then we multiply this, so we multiply the entire equation by sine inverse of x. So this goes here. So we have sine inverse of x onto 1 over sine inverse x dy by dx equals to 1. So to do that, this and this are going to cancel out. We're just going to be having dy by dx. Just going to have dy by dx is equals to this and this is sine inverse of x. So dy by dx equal to sine inverse of x. Great. Once we've done that, the next thing we could do is to separate variable right there. Separate variable right there. So how do we separate the variable? We multiply this side by dx. So we have dy is equal to sine inverse of x dx. Once we've done this, we can integrate both sides. So we have the integral of dy is equal to the integral of sine inverse of x dx. But you know something very important. Remember, we want to find y and compare that with this. That's the essence of the entire stuff. So we know the integral of dy is just y. So y is just equals to the integral of sine inverse of x dx. So we want to integrate that inverse function. To do that, we will have to do something very important. And what is that? We're going to use integration of paths to integrate this. So if you have y is equals to the integral of sine inverse of x dx, you can say let u equals to sine inverse of x and then dv equal to dx. So u equal to this and dv equal to this. If you differentiate, you have du is equals to the derivative of sine inverse of x is 1 over the square root of 1 minus s squared. And then if you integrate dv, you integrate dx. Remember, for integration of paths, we differentiate one side and then we integrate one side. So the integral of dv is just v, integral of dx is x. So move on to evaluate this. So I'm just going to write the integral of u dv. Integral of u dv is equal to uv minus the integral of v du. This is the integration by parts expression. That's the equation. This is the equation used for integration of parts. I'm just going to write that. And then once I'm done with that, I'm going to write y is equals to. Now this integral is equivalent to the entire thing. So we have uv. uv multiply u and v. U is this, v is this. So sine inverse of x times x is x sine inverse of x. And then we have minus the integral of v du. What is v? V is x. Remember, du, you have to differentiate so you have to get the s there. So du is dx over the square root of 1 minus s squared. That's what we have. So v du, v times this is going to give you this. Now, we kind of don't know directly what is this integral, so we have to use a substitution, or call it u substitution. So we say let u, right here, I'm going to use red marker. Right here we say let u equals to the square root of 1 minus s squared. If we differentiate, we have the u is equals to, in fact, we cannot differentiate just like this, so let's square both sides. We have u squared is equals to 1 minus s squared all squared. That's what we do. We square both sides. And then once we are done squaring both sides, we can simplify. Remember, this one is square root. This one is square root. So u squared is equal to 1 minus s squared. Differentiate 2u du is equal to minus 2x dx. The derivative of 1 is 0. The derivative of negative s squared is minus 2x dx. So we can divide this out by 2 and divide it by 2. So what we have? We have u du is equal to minus x dx. Great. So we say we want to evaluate this. So let's move to this side and then evaluate that. So that's what we should do. Find L of x. Great. So we have u du to be negative x dx. So let's rewrite this expression. We have y is equal to x sine inverse of x. What happened? We have u du to be negative x dx. But here we have x dx. What is the negative? So take this negative inside. This negative goes inside. We are going to have plus the integral of negative x dx, all divided by the square root of 1 minus s squared. So I'm just rewriting this. I have not done the substitution yet. I'm just rewriting it. So let's go now and do the substitution. So we get y is equals to x sine inverse of x plus the integral of negative s dx is u du. So it's u du all divided by this entire expression. U is the entire expression. So the entire thing is u. So we have y is equals to x sine inverse of x plus, then they are going to cancel out, so you're going to have the integral of du. So y is equals to x sine inverse of x plus, what is the integral of du? It's just u plus c. But what is u? What is u? So we say but u is the square root of 1 minus s squared. The square root of 1 minus s squared. Great. So what do we have there? We have y is equal to x sine inverse of x plus the square root of 1 minus s squared plus c. That's what we have. Now, that result we just got, we have to compare that result with the actual solution given. So if the solution of this differential equation is this, find L of x. So let's compare. We have y, we have equal x sine inverse of x sine inverse of x plus L of x, the square root of 1 plus 1 minus s squared, and then cc. So what is L of x if you do this comparison? Therefore, L of x is the square root. So L of x is this, the square root of 1 minus s squared. Thank you very much for watching, and we hope to see you in question number 16. Good day. So thank you for coming back to our channel. As you can tell by the title, we are going to be verifying as to whether a particular solution is a solution to a given differential equation. So show that y equals a cos x plus b sin x is a solution to the differential equation y prime prime plus y equal to 0. Now, grab yourself a cup of cold water, sit back and watch as I drill you through the process of verifying this. Good. So the first thing we do is to take the function given. Take the function, so I'm going to say solution. We take y is equals to a cos x plus b sine of x. Now we could do two things here. We will actually differentiate this thing twice and replace the value here and see as to whether the left hand side is going to be equal to the right hand side after substituting y prime prime and y here. So we differentiate two times, substitute y prime prime and y, and then simplify to see what will get 0. If we have 0, it means that that solution is actually a solution to this differential equation. Another thing we could do is to eliminate the arbitrary constant from here and see what differential equation will we have. If we eliminate the arbitrary constant from here and then we have this differential equation, it means that this is a solution to this. Now, most of you can already tell because if you find the characteristic equation for this and then you write the solution, you're actually going to have this. Some of you can already tell, but let's just go through the process. So we differentiate the first time we have y prime is equal to the derivative of a cos x is minus a sin x. Remember, the derivative of cos x is negative sin x again. Plus, the derivative of b sin x is b cos x. Straightforward. Easy, right? Good. We move on and find the next derivative. So y prime prime is equal to, what is the derivative of negative a sin x? We differentiate sin x, that's cos x. So it's negative a cos x. And the derivative of b cos x is negative b what? Sin x. Because the derivative of cos is negative sin, remember? So when we do this, this is the second derivative. We can take this and this and add them to see what will get 0. Obviously, we add this and this because this is y prime prime plus y equals 0. So y prime prime plus y, we add this and this, they are going to cancel out. This and this are also going to cancel out. Because all of them cancel, so you have 0 equals 0. That's just one method. Another method is to factor out a negative 1 from y prime prime. So factor out negative 1. We have factor out negative 1 here, we have a cos x plus b sin x. Good. But we know very well that a cos x plus b sin x is y. A cos x plus b sin x is y. So this entirety is going to be y prime prime is equal to minus 1 times y. Or y prime prime is equal to minus y. So if you have y prime prime is equal to minus y, how do you solve to prove that this and these are going to be equal? You send this across. So you have y prime prime plus y equals 0. So because we eliminated the arbitrary constant from here, and then we have this differential equation, we can conclude that this solution is a solution to this differential equation. Thank you very much for watching, and hope you subscribe to our channel for more amazing videos.